Hi, everybody. So in this particular sequence of videos, we're going to talk about basis again, just to review, and we'll talk about dimension. And then finally, we get into the coordinate theorem, which is our bridge between what we learned in Rn spaces and what we learn now in general vector spaces. So if you have a vector space and B is some subset of V, we say that B is a basis for V if and only if that it spans the space and it's linearly independent. We're going to assume, like I did before, that every single vector space has a basis. And notice that the basis need not be finite because we're insisting on using linear combinations, where in the definition of linear combinations, we insist that we only use a finite linear combination. So you can't just add up an infinite number of vectors. Just as a review, the various vector spaces have standard bases that we refer to. We often call them the basis E, if we need to say such a thing. The standard basis for the set of all polynomials of degree n or less is the set 1, x squared, up to x to the n. It's obvious they're independent. I showed that before, and it's obvious it spans the space. I showed that before. So then this is definitely a basis for Pn. And then the matrices E sub ij, where in the ith jth entry of the matrix is 1 and everywhere else it's 0. Those m times n number of matrices is the standard basis for the set of matrices that are size m by n. And again, I already showed that these matrices are independent, and it's incredibly obvious to show that they span the space. So they're a basis for that vector space. Now, sometimes though you're given a subset or the set is described in some kind of algebraic way, and you want to know what's a basis for the space. So I'm giving you two spaces. You should notice though, they're kind of similar. You have A, B, B, negative A for the entries of W for the matrices. And for W, the polynomial, the set of polynomials, it's A, B, B minus A, where I'm only talking about the coefficients in front of 1, x squared, and x cubed. So there's definitely a similarity between these two. So you expect that if you want to know the basis for these two spaces, there's probably a connection between them. And in fact, notice that on the left, you can write the matrix A, B, B, negative A. You could rip it apart in terms of a matrix of A's and a matrix of B's, and then pull the scalars A and B out to get this expression. The same can be said for the polynomials. Notice on the right-hand side, you can kind of gather up all the terms that have an A, all the terms that have a B, and then pull the scalar A and B out to get that. In this case, this particular polynomial can be written as this linear combination of these two vectors. So therefore, that means then on the left-hand side, W is spanned by these two matrices, U and V. And on the right-hand side, W is spanned by these two polynomials. And again, notice there's a connection between the vectors I have on the left for the set of matrices and the vectors I have on the right for the set of polynomials of degree 3 or less. And also notice it's pretty obvious, those two vectors on both sides, that they're independent of each other. They have to be linearly independent because they are not multiples of each other. The only way that two vectors can be independent is if they're not multiples of each other, and they're not. Neither one is a multiple of the other. So they span the space. They're linearly independent. They are bases for their corresponding vector spaces. And again, notice there's a deeper connection between these two things. All right. So the next thing is that if you have a vector space and you have a basis of n vectors, then every vector in V can be written exactly as one linear combination of the vectors in the basis. This is a theorem I proved before. It's the exact same proof now. I'm not interested in doing so. I am interested in using it though. So the way we use it is we define, like we did before, the idea of coordinates. If you give me any vector in a vector space and you have a basis of n vectors for that vector space, then the vector has a unique linear combination of the basis vectors that adds up to the vector V. The coordinates are the scalars used in order to form that linear combination. Those scalars are unique. They are associated with the vector. So we write the coordinate vector with a V with brackets around it, and we write in a subscript what basis we're doing the coordinates relative to. And then those coordinates are usually just written as a column vector of real numbers, where the real numbers are just the scalars you need to form the linear combination of the basis vectors to get to V, Now, I'll give you a couple examples so you understand what I mean. But one nice thing we get is that also from the previous theorem, remember that relative to a basis, the coordinates are unique. That means that if you have two vectors in V and find their coordinates, if the vectors are equal, the coordinates are equal. Also, again, if you have two vectors in V and their coordinates relative to a basis, I'm not saying which one, but relative to a basis, if they're equal, then the vectors must be equal. And that's because vectors have unique coordinates relative. Every vector can be written as a unique linear combination of the basis vectors. So we have this nice connection between the two. We can look at the vectors in U in the vector space V, or we can look at their coordinates instead. So just as an example, so you understand what I mean by coordinates with numbers. Let's find the coordinates of this vector. Notice I made the whole thing boldface to emphasize that's the vector. I want to do relative to the standard basis 1x, x squared, and then I'm going to do a relative to the basis b, x squared, x1. B is not called the standard basis, although obviously they look the same because one is just a reordering of the other. E is usually referred to as the standard basis, the order 1x, x squared. It does make a difference. You'll see. Let's find the coordinates of this vector relative to these two bases. So relative to basis E, the vector -1 plus 3x plus 2x squared relative to E would be the column vector -1, 3, 2. Because by definition, if I use these scalars in this order as a linear combination for the basis E, I should get the vector -1, 3x plus 2x squared. And indeed, you see, I do. Now, what if I want to find the coordinates relative to B? So again, the same vector. I want to find its coordinates relative to B. That would be a column vector. Would have to have 3 entries in it. And the entries are 2, 3, and -1. That's because if you use those scalars in that order for basis B and add up that particular linear combination, you'll get the vector -1, 3x, and plus 2x squared. Notice that the order that the basis elements are in does make a difference. The order the basis vectors are listed in the set do make a difference. You do not get the same answer. Okay, so let's do another one. What if I wanted to know what are the coordinates of the zero polynomial, the zero vector, the zero polynomial in the set of polynomials of degree 2 or less? Well, notice though that if you want to, you could take 0 times the vector 1 plus 0 times the vector x plus 0 times the vector x squared, and that would then equal the 0 vector. Well, now the 0 vector here, I'll put a little vector notation. That 0 vector is in P2. It's the polynomial that assigns to every single real number 0. And if I want the coordinates of it relative to the basis E, that would be the vector 0, 0, 0, which is the 0 vector, where this is in R3. And we know that since the coordinates are unique, this is the only answer. So the 0 vector in P2, its coordinates are the 0 vector in R3, and vice versa. If you have the coordinate vector 0 in R3, it corresponds to the 0 vector in P2. I think you can pretty much see then that's actually always true. You give me any vector space that has a basis, and you want to know what are the coordinates of the 0 vector for that vector space V, it's always the 0 vector in Rn, assuming that the basis has n vectors. Okay, so then one last one. You need to see something a little more interesting. So let's go back to that vector I gave you before, -1, 3x plus 2x squared. And I want to find its coordinates relative to this basis, D. So we know it's a basis. So that means that the span of these vectors is all of P2. That means then that the vector -1, 3x plus 2x squared, that vector has coordinates relative to this basis. It's just to find it. So those coordinates would then be C1, C2, C3. That means then that the linear combination of the basis vectors using those scalars in that order would have to add up to the vector -1, 3x plus 2x squared. Well, on the right-hand side, let's just kind of add everything up. So if you add everything up using like terms, you would get this. You'd have the scalar c1 plus c2 plus c3 equals 1. You'd have c2 plus c3 equals x. And you'd have c3 plus times x squared. Well, the only way that's true is if the corresponding scalars on both sides in front of the basis vectors 1, x, and x squared are the same. And the reason is on the left-hand side, don't think of it as the vector. Think of it as -1 times the vector 1 plus 3 times the vector x plus 2 times the vector x squared. So then this would then be a linear combination on both sides in terms of the basis vectors 1, x, and x squared. We know that the linear combination has to be unique. So therefore, this scalar has to equal that scalar. This scalar has got to equal that scalar. And then this scalar has to equal that scalar. Again, that's because that relative to the basis 1x, x squared, that the coordinates are unique. So these two vectors are linear combinations of those vectors. So the scalars must be the same. So that means you get that system. Now notice by doing this little trick, we are right back to what you're used to. This is now just a linear system in 3 unknowns. I would solve it using back substitution or using some other thing, using Gaussian elimination or using matrix inverses, Cramer's rule. There's all kinds of ways to do it. Here, they'll just write down the answer. So that means then, if you want to know the coordinates of the vector -1 plus 3x plus 2x squared relative to the basis d, it's the vector -4, 1, 2. And that's it. I believe that's enough for that portion of the video.